Jnanam Paramam Dheyam. Knowledge is supreme.
Welcome to today's lecture on advanced transition metal organometallic chemistry. We have been discussing transition metal arene complexes in the last few lectures, and in particular we have spoken about various synthetic methods that are available for synthesizing these transition metal arene complexes. In our last lecture, to start with, we have discussed Fischer-Hafner synthesis, which involved reaction of metal trichloride with aluminum in presence of arene, and these gives this transition metal arene binary complexes. This method is quite general in the sense that many transition metals can be used for synthesizing bis-arene complexes using Fischer-Hafner synthesis. The other method that we discussed, this cyclotrimerization of arenes. In these reactions, trimerizations of alkynes occur in presence of some metal template, resulting in transition metal arene complexes. And then we have also discussed the third method, which is reductive complexation. This is an interesting method in the sense that the method involves ligand which could form radical anion, and then the reaction of the radical anion salts with transition metal halides, giving these binary transition metal arene complexes. So, these are very interesting methods for preparing these binary transition metal arene complexes, and we are going to continue this discussion further by looking into some more examples of these transition metal arene complexes in this lecture today. So, one such important method is this metal atom ligand vapor co-condensation reactions. These are called metal atom ligand vapor co-condensation. Reactions are better known as CC reactions. Actually, in this method, metal atom in its vaporized state is directly reacted with ligand vapor and then cooled to very low temperature, in which all combinations of compound that can possibly form results, and then after workup each of these compounds are isolated and characterized. This method, however, is very useful for producing a variety of bis-arene complexes which otherwise would be extremely difficult to synthesize, and we are going to take a look at some of the interesting compounds which utilizes this method to produce certain bis-arene complexes which otherwise would have been very difficult to synthesize. Now, this method was sort of propagated or developed and propagated by and large by Professor Malcolm Green and Jeffrey Cloak, and so they have done a significant advancement in developing this method and popularizing this method. So, for example, complexes like this R equals hydrogen, then metal equals titanium, niobium, molybdenum, and R equals T butyl, then metal equals titanium, zirconium, hafnium, scandium, terbium, Gs, Dy, HO, E, R, Lu. So these are a large variety of these bis arene complexes which are synthesized by this method. We are going to take a look at some more interesting examples that have been synthesized using this method. For example, the halide complexes like this, or the amide complexes like this, here metal is chromium and molybdenum. Similarly, sandwich cyclophane type compounds, this distance, chromium arene distance is 290 picometer, whereas the same which is much smaller than the chromium arene distance is bis benzene compound. In this case, where this is about 322 picometer. This distance at 290 picometer is the distance between the two rings, and over here this 322 picometer is the distance between the two rings. So what one sees that there is a compression arising from the presence of this ethylene bridge in the cyclopentadienyl ligand. Now, there is another interesting system which is a biphenyl ring, where both of the iron rings are directly metallated, giving some structure like this. And one interesting thing about this compound is that this compound in solution can exist in monoradical cation state. In solution can exist in monoradical cation state with each chromium plus half and chromium plus half oxidation state. So this is interesting complexes. Also, this method was effectively used for preparing neutral sandwich complexes of annihilated first 6-membered rings. Effectively used, CC method was effectively used in preparation of neutral sandwich sandwich complexes of annihilated 6-membered arene arenes. So, let me just give some examples of these types. These are really there are really some interesting examples. So, M equals vanadium chromium. One can even extend it further through 3 rings. Now, here the complex formed is of this type, as well as another interesting example include chromium, okay. Now, of these are very interesting complexes where we have these annihilated 6-membered ring complexes of various arene. Now, while these complexes are synthesized and characterized the way it is shown, the interesting bit about it is that in higher annihilated arene, which of the rings, if there are more than 1 6-membered rings are present, which of the ring would really be coordinating to the metal. So, the question primarily over here is that let us say for example, in these there are 2 arene rings, for these there are 3 arene rings, for these there are 4 arene rings. The question is that which particular one would be forming these bis arene complexes of with chromium, and is there is this just by coincidence, or is there any rule which governs them? And in fact, this has been studied extensively, and the reason which has been given out is the ring which has the maximum highest index of local aromaticity, that ring results in formation of these bis arene complexes. So, let me just illustrate this in bit more details. In case of higher annihilated arenes, the metal atom coordinates to ring with highest index of local aromaticity. And this is ILA, index of local aromaticity, and this is explained as the ring that among canonical forms most frequently appears with a cacule that means aromatic sextet structure. So, this is an interesting observation. What it says that when you have annihilated rings where there are multiple 6-membered arene rings conjoined together, then the question is which of this ring the metal would coordinate to, and the answer to that is the metal prefers to bind to the aromatic ring which will have highest index of local aromaticity, or rather which is popularly known as ILA. And ILA means that the ring, when you draw the canonical structures of this whole conjugated system, that the ring which will most frequently appear in the caculous aromatic sextet structure, that is the ring which would ultimately end up binding to the metal. So, let me just show some structure and their preferential binding. For example, if this is 3 6-membered conjugated ring, then M is the one which on the side on ring, that would be the one which would be binding to the metal. Similarly, for structures like this, the metal would bind to the first side one, or when the structure is like 4 rings like this, the metal would bind to this one, and if it is something like this, the metal would bind to this one. So, this is an interesting observation which explains a variety of structures that arise by this co-condensation method. This method obviously is a very useful method where one can synthetically get access to very interesting compounds which otherwise using preparative chemistry may be extremely difficult to synthesize. With this, let me just move on to the structure and bonding in this bis arene complexes, and these we are going to be looking at the structure and bonding with respect to its molecular orbital diagram. So, in the beginning, let us sort of look at how these atomic orbitals combine to form these fragment atomic orbitals for the arene rings, and then move on to system which is more complicated, like bis arene interacting with the metal, and then look at the interaction at the metal level. Now, as far as the bis arene complexes structure and bonding, this also is somewhat similar to the cyclopentadienyl ligand, where the pi orbitals engage in bonding, and let us sort of take a look at the different combinations of pi orbital that can result in various FMOs, and then see how they orient and themselves prior to their binding to metal. So, for the benzene, and we the simplest constructions that we would do is for benzene, we are going to draw the structures of different molecular orbital, and The first obviously is the all bonding orbital, which is A2U, and in this all there is 0, all the nodes are at the bottom the way it is shown. Similarly, the first degenerate pair is E1G, and here one has 2 orbitals, the first one has molecular orbital of this type, where and the corresponding the nodal plane is shown over here, and the other form is somewhat like this, and the corresponding nodal plane is given as this. The next is E2U, this also have 2 degenerate FMOs, and the first one is something like this, so this has 2 nodal planes, one along this and another along this, and the other one is this, and this also is degenerate to the top one and has 2 nodal planes, one along this, the other one that, and the last orbital is somewhat like this. It has alternate lobes of opposite faces and has 3 nodal planes. And this one is called B2G. Now, these gives a feel for how these individual pi orbitals are oriented based on their energy, and before they stack up with bis benzene or bis arene prior to they finally interacting with the metal orbital. Now, if you look at these benzene atomic orbitals, you see there are 6 pi orbitals. So, there should be overall 6 fragment molecular orbital in combination, and we do have 6 over here, 1, 2, 3, 4, 5, 6, and of the 6 the distribution is, the first one is fully bonding with 0 nodal plane. The second one is a degenerate 2 orbitals with singular nodal plane, and third one is also a degenerate doubly degenerate 2 orbitals with 2 nodal plane, and the third one the fourth one is the most high energy antibonding orbital having 3 nodal planes. So, we have seen how these pi orbitals sort of combine themselves to give 6 fragment molecular orbitals. This is somewhat similar to what we had seen for cyclopentadienyl anion, where it was E1 and E2 combinations. So, that was just the 6th orbital which is present over here was missing for the cyclopentadienyl ligand. So, with this I am going to conclude today's lecture. We have been discussing on the synthetic methods available for synthesizing these bis-arene complexes, and particularly to begin with, we have looked into this fancy method which is called metal atom ligand vapor co-condensation method, or CC method in general. This method is a very useful method for preparing a wide variety of bis-arene complexes. We have looked into some of the examples of this method and had seen that how this method was successfully used in preparing these complexes. Also, we had observed that in case of at large higher annihilated ring systems, it is the 6-membered ring which has highest local aromaticity index ILA. That ring was particularly found preferably coordinated to the metal in the bis-arene binary arene systems. We have also looked at the structure and bonding of these bis-arene systems, and to start with we have looked into how the p orbitals of benzenes orient themselves to form the fragment molecular orbitals, which are A2U, E1G, E2U and B1G, containing 6 set of orbitals depending on the nodal plane that arises out of their combination. So, with this we are going to stop in today's lecture. We are going to take up this structure bonding in much more detail, where we now look at the concepts which are developed over here and now see that how this A2, E1G, E2U and B2G finally interact with the metal and study its correlation diagram, which eventually we will construct using this fragment molecular orbital. So, we are in the midst of a very interesting discussion on bis-arene complexes, its structure and bonding, and we are going to be continuing this in the next lecture, where we develop or construct this molecular orbital diagram using these fragment molecular orbitals that we have developed over here. So, till then I really thank you for being with me in this lecture, and hope to see you in the next lecture, where we are going to be discussing structure and bonding of bis-arene metal complexes in greater details. Thank you.